Okay, thanks. Super.
Okay,
Thank you.
so I will ask you a very specific question first. What exactly is grasping? Okay, and before you answer, I'll show you this clip. Okay, I'll share my screen and I'll play this video for you to watch. I hope you can see that. So, can you identify the organism here? I'll play it again at the beginning. So, this is a single cellular organism called an amoeba, right? We all know it's an amoeba. And the amoeba is, can we call it grasping? That's the first question. And, it would be great, for you to respond and, we can discuss this to begin with.
Madhura, what is the question?
Can we call this behavior grasping?
Yeah.
Okay, so we agree that grasping is more about, getting hold of something than about the hands,
Mhm.
right? So,
Yes.
so, so, so one can argue that amoebas can grasp, right? So grasping is not a uniquely human or uniquely a trait that, that arose at any particular point in the evolutionary history, right? Like when such organisms can actually grasp, right? So now then so if we agree to that, then when we say that we are trying to understand the neural correlates of grasping, let's say in humans, what exactly are we trying to understand? Are we trying to understand the behavior to grasp, and do we really think that all the neural substrate is required to grasp? Or we need much more neural substrate because we have a different, appendage, a hand, which is much more complex and a lot more constrained. So we now need a lot more neurons to deal with those constraints, right? So whether we believe this is grasping or not completely changes how we, approach the question of grasping in humans, for instance. Okay. This first example. I'll show you a second example, which is one of my favorite organisms.
Dear winter, our SWAT of vehicles with all-wheel drive and full.
So
And
this is a
that other clade includes basically every bug, insects, arachnids, even crustaceans and trilobites. The organism that branched away from tardigrades has literally millions of species as its ancestor, but the branch that tardigrades sit on, just tardigrades. Though there are over 1,000 described tardigrade species, and there are likely many times more than that out there. But nonetheless, they do look a lot like bears with their claws and stumpy 4 pairs of legs. Tardigrades hover right on the edge of microscopic. They range widely in size from 50 microns long to 1,200 microns, but usually they're under 500 microns in size. Tardigrades can be found in 3 major aquatic environments. Some live in marine or brackish water, others in fresh waters, but them look super cute. They also boggle the mind because they aren't eyes. To be an eye, you have to be an organ. And to be an organ, you have to be composed of tissues that are themselves composed of cells. But each tardigrade eye is, in fact, a single photoreceptive cell. That is wild. On their whole body, sometimes containing tens of thousands of cells, they have 2 cells. And those 2 cells are their 2 little eyes.
So you see, now you have tardigrades who look like bears, right? That's why we call them water bears. They walk like bears. They have 4 legs, right? They have a so-called gait. Okay. Now we don't know what's inside the legs. Basically, it's mushy fluid. They don't have bones. They don't have cartilage. but they have very characteristic gait, which look like a gait of bear. You can basically impose a skin of a bear, and people will be having difficulty to understand that.
Madhur, for some reason we hear you more quiet now than before.
Okay, so what I'm saying is these tardigrades are called water bears for a reason, that they look like bear, right? So when they walk, the gait resembles the gait of a bear. And you see they have two eyes, which are nothing but single photoreceptors, right? So an eye is an organ, but they have two photoreceptors which work as well in their environment, for them to navigate. So then again, this example flips our questions when we are interested in hand-eye coordination or coordination of walking. We cannot attribute these characteristics to humans or to other organisms, so-called higher in the evolutionary ladder. Very simple organisms like tardigrades show very complex behavior just with two photons, right? Two photon receptors, which are two cells, and with legs, which are nothing but extension of the same material of which the body is made. Okay, with a little bit of more rigid tissue there. I won't go into the details, but tardigrade also have claws. And if you look at a amputated human with a old kind of prosthesis, which had nothing but hooks, right? When we did not have very advanced prosthesis, tardigrade claws resemble very much like that and function very much like a human, with a lost appendage. So now the question is like, what exactly is locomotion? Is it about dealing with the constraints of what the body is, or is it about moving in a certain fashion? Okay. So I'm just recasting that question. And then I'll give you a third example, which is, now can you guess what I have on my screen on the left? And what I have it on the right?
On the right, you have a X-ray of a foot, human foot.
Yes. And on the left?
Also an X-ray of it.
An X-ray of a very old foot.
On the
we
left,
know
you have the cross section of an elephant foot.
Oh.
So the elephant foot, which looks like a cylinder from the outside, has a very, very similar structure as a human feet. Now, what's interesting is that a human can put heels on, and then the structure of their bones would resemble the structure of bones inside an elephant feet. Okay, so we do have functional similarities, at certain scales, resembling with with elephant foot, even though we treat elephant gait differently than human gait, as well as we think about elephant feet differently than human feet. So with these examples, what I'm trying to get at is that our conceptions of functional behavior and our conceptions of the role of anatomy for those functional behaviors is not very clear. There's a multiple realizability issue. We can have different forms behaving the same way, and we can have different the same form, behaving different ways. The question is that how are these objects, which are at very different scales, starting from an amoeba, which is basically a fluid, to what we are tardigrade, to humans and elephants, what aspects are they different and what exacts are the same? And then it also recasts the role of cognition and the role of all the central nervous tissue, what we have. How should we look at it? What's its role in coordination? So I'll go back again. Now, if you think of grasping in amoeba, what exactly it is changing? One thing which we see is that when an amoeba grasps, the amoeba is no more the same amoeba. The boundaries between amoeba and environment change in ways which are different than how it changes in us, for instance, when we grasp. When we grasp, we are able to still maintain some functions of the body discrete from that grasping, right? And return to those functions, which is not the case in amoeba, where every action of grasping completely changes its properties, for the next, whatever it does next. So we have a lot more a lot more ability to preserve functions, to be more resilient to our actions, basically. So we are more stable, and our own actions are resilient to our own, upcoming actions. We can nest those actions. That's not the case with an amoeba. It's hard to nest those actions across different scales because the amoeba itself is changing while behaving. Now, why, if you think of mouth, for instance, a mouth can also grasp. We think of grasping and we think of hands, but if you don't have, you're grasping with the mouth, right? And when you look at animals who are walking on four legs, they are basically grasping mostly with their mouth, eating directly with the mouth, right? Now, what exactly the distinction between hands and mouth does? Like if you remove grasping to the hand and then you eat with the mouth rather than doing both with the mouth, it lets you uh, free up your, evolutionary speaking, your attention. You can focus on, you know, more food in the future, more food in the environment at different spatial scales while you are currently feeding, right? So and we can trace each of those distinctions between the current function or the nesting of different functions, as well as the ability to create a boundary between us and environment, across these different scales, to basically different evolutionary pressures and put them in a more evolutionary light. So so now the question becomes, why are we comparing these organisms? So just to summarize, these organisms are at vastly different scales. They have very different anatomies. They're very different complexities of nervous system, from almost no nervous system to a very complex nervous system, the most complex that we know. Uh, but across all these scales, what we have common is basically a fluid-like property in their ability to sense, move, and adapt. Rest all is different. That capability is the only thing which is similar. So you have amoebas, which are single cell, basically fluid, show adaptive behavior. You have tardigrades, which are more resilient than amoeba. Okay, they have more hydraulic control of limbs, but they do have gaits which are more fluid-like. You have elephants who have much more non-linear gaits. They have more social behavior, which influence their movement patterns. And then you have humans, which are even more complex in terms of their movements and their ability to do things. When you look at the connection between those movements and cognition, how we understand, amoebas are showing, emergent intelligence, especially when you think in terms of energy gradients. If it is all about the ability to sense energy gradients, amoeba is doing pretty well, right? And we don't do much differently. We are sensing the gradients of food, the gradients of mates, or the gradients of, job opportunities. I mean, everything can be casted in terms of gradient, and depending on how complex that gradient is, we have, or at what scale those gradient function, we have a system catering to those gradients. But that fluidic interactions and that fluidic interactions governed by gradients is a commonality across all of these scales. Okay. Uh, so 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 this is something which keeps me awake. That what exactly are we missing? When are we being very exclusive about the human body? And when exactly are we talking about actual biology and actual continuum across the evolutionary scales? So now the challenge is to frame this common framework, and the next step, which is once we frame it, how do we go ahead to address the questions we are interested in using this framework? So this framework instantly, forces us to uh, embrace a fluid dynamical approach as a basis for motion across scales. And I'll talk more about this later. So amoebas are doing it by controlling their internal cytoplasmic flow, similar to how muscle contractions create complex motions in humans. In fact, you can simulate a dry amoeba where you change the fluidic properties of an amoeba and you see disruptions in its movements. For instance, you can freeze the liquid in which amoeba is, or tardigrade is, and you see less of motion. And ironically, we call the inability to walk or the inability to move freely. In Parkinson's, for instance, freezing of gait, right? The effects are not very different. You can actually create a, a Parkinsonian model of movement in tardigrade just by changing the temperature of the fluid in which it is surrounded. Elephants have soft tissues, so they deal with musculoskeletal loads differently, very similar to how we move. And we have even more different locomotor strategies, given the kind of flexibility we have and the ability to load things differently. Now the question is that when does an amoeba, like where exactly is the boundary between amoeba and tardigrade, and where's the boundary between a tardigrade and a human? Is it the bones which make us different than tardigrade, or a bear different than a water bear? Or is it the neural control of those bones or the joint receptors? Like, what exactly is the distinguishing feature between the two kinds of control of gait when gait apparently looks the same? Okay, that's a big question here. And now, what exactly is cognition? Cognition can be from these contexts can be reframed as. And by the way, as a disclaimer, this is all shared knowledge. I've synthesized a little bit of that, and I'm not quite posing these questions for the first time here. So amoebas solve the problems without a brain. They can navigate chemical gradients. Tardigrade, they also adjust their movement strategies based on water availability, water temperature, the solutes in the water. So they also show some kind of biomechanical intelligence. Elephants rely on, more social aspects. They show much more complex biomechanics, which is determined by factors other than, just the flow of air or the fluid or the surface on which they're standing. And humans also show similar behavior. And in diseases like conditions like stroke and diseases like Parkinson's, we show loss of adaptive fluidity, suggesting that cognition and motor control are deeply intertwined. Probably the same thing. Now, if you think about human bipedal stance, for instance, bipedal stance is not natural. It takes a lot of effort to walk bipedally. In fact, it's not like our basal state. So it takes a long time for a kid to stand bipedally because starting from reflexes to muscular strength to neuromuscular control, to be able to balance the body, to be able to not just balance, but direct attention to something else while you're standing, to be able to deal with the perturbation, which can basically make you fall while you learn walking or walking later. There are a lot of challenges to walking. It's not normal, and we are the only species which walk. And it is so not normal that the body is actually, when we are born, it is not even made for that. So the muscles, especially in the neck of a newborn infant, are very weak. In fact, some infants end up developing a condition called torticollis, in which the muscles do not develop as well as they should, and they show a head tilt, and they need extreme intervention to be able to just sit. Standing is even a larger challenge. So there's a lot more challenge, and our parents have to do a lot for us to be able to walk. Well, and that's not very different when we grow up. When we grow old, and if you look at Parkinson's, what does that affect first? The first thing it affects is our ability to stand, right? So it's the most challenging aspect for a Parkinson's patient, and any other condition as well. The instant damage we have is to our standing capability. In fact, we don't stand when we faint. As soon as we faint, we basically fall. There are as many reasons to fall, as many ways we can fall. So standing and bipedal posture is not common to us. It's not natural. I can skip this probably because it's already in the article. But ironically, when you look at, I mean, just a pun on our lifestyle, but here we are, just to show you again at different scales. Again, standing is not natural. We have a propensity to come back to a sitting posture or to a lying posture. We don't need to put effort to stand and walk. Okay, that's not. what we are naturally inclined to do. So walking takes a lot of effort. Now, when you look at, okay, so let's have some interactions here. Like, am I clear? And do we have any questions so far, or do you follow the trail? What I'm trying to come at?
One question that we can take some questions now. Yes. I can start. One question that came to me is, why do we have bones at all if all this could be sort of fluid?
So I wouldn't say that bones is not fluid. I would say it allows us to have more non-fluid or to modulate our fluidity more, right?
Yes.
So
So is it that you showed it? I mean, it was a very nice sort of mind trip, really, to think about movement from the fluid dynamic side and not from the side of the dynamics of rigid bodies, how we usually think about it, right?
yeah.
But then the question is, okay, so is ossifying and sedimenting making us more resilient, or what is it? How, I mean, if we are asking such general questions, Suzanne says it's gravity, but is it? I mean, I don't know. Maybe.
Who knows the answer? I don't think we know the answer. But the thing is that, when I discussed that the amoeba, when it's grasping, it's not able to differentiate itself from its action, and it's not able to maintain uh, parity with the upcoming actions, and not able to nest. Uh, uh, each and every action is basically it's hard to have a nested sequence of actions for an amoeba, right? The less fluid you are in the sense of calcification, the more it allows us to nest across scales, actions across scales, and to maintain a sort of functional independence of body parts, or organization, when a whole sequence of action unfolds. But at the same time, it can go to the other extreme where you have too much of calcification when it hampers the transitions to those nesting events, right? And we know conditions, not necessarily by greater calcification, but by greater functional ossification, which happens in Parkinson's, for instance. And we call it basically less fluidic. We all understand metaphorically that those movements are less fluidic, or as well as less flexible, right? So we can talk about ossification at the level of anatomy. We can also talk about ossification at the level of function, right? So that's one of the advantages of ossification through bones, for instance. If that answers, at least partially, right? So that nesting is important, and I think a lot of changes can be understood more in terms of its ability to nest across larger and larger spans of scales. Okay. Now, it's very easy to think of ossification of bones because we can visualize, from tardigrade to human, for instance, leg or a bare leg, we can think of a difference in terms of bones. But there are other differences as well in terms of how a tardigrade might be planning its action or not, or how whether, for instance, I mean, the question is like, what kind of organisms will suffer Parkinson's, or what kind of organisms will have similar kind of conditions that humans have because of, let's say, changes in bone density. Is there any similar kind of condition in an organism like Parkinson's? Okay. What should aging look like for an amoeba? Right. Do we have a grandfather amoeba? Okay. So those are the questions I think, if we think harder, we might get at some important answers. But again, this is fun, and this is for pontification. Okay. So, any other questions?
I have some.
Yeah.
So what would you think about of somebody who has Parkinson in space? Would you think that this would affect the person or not?
A very
So,
beautiful question. So okay, and when you think in terms of the way we think of biomechanics and human motion, as if we are controlling the joint angle and the joint coordination, versus when we think of body as a fluid and we are trying to control its trajectory in another fluidic space, it kind of changes. So I really do not have the exact answer for that, but I think it will not be as affected. So it depends. I think in some things it will make it even more difficult because you need much more internal control when you do not have external constraints. So for instance, we know the case of HM, not HM. The person in the book Pride in a Daily Marathon who lost all proprioceptor receptors, right? So he had to use vision to stand. And Michael Turvey has talked a lot about, and I think has met this person as well. Ian Waterman, that's the name. Okay. So, yeah, you got me more raging, in my head than actually, being able to come up with an answer for that. I think it will make certain conditions worse. It will improve on certain other conditions. It depends on what we are talking about and what kind of constraints we are talking about, whether we're talking about locomotion or we are talking about general ability to move or something like that. But it's a very, very interesting question. And I also think that our current methods, biomechanical methods, are not sufficient to answer those questions. If you think about it, when you swim, the body doesn't move the same way when we do on water, on while we are walking, on the ground surface. So, and one can study that as you increase the buoyancy, for instance, in an underwater treadmill, people behave more and more like a jellyfish than actually they do like humans. They have less control over gaits. They give away more of the control, or they're more in terms of a relationship with water than they are on the ground surface. So, yeah, I think so. From that perspective, it should help to be in space for Parkinson's patients. Okay, maybe we can have in the future we can have a planet with low gravity. So once you have Parkinson's or once you have some kind of neuromuscular weakness, you move to that planet with a little lesser force of gravity. So yeah, hopefully I've had just some of your curiosity there. Okay, so not tool use. So let's come back to tool use a little later regarding in the context of this publication which I've shared with you all. But let's go with some of the assumptions about the human movement system and how changing some of those assumptions and identifying the limitations and probably embrace some new assumptions can help answer some of these questions. So one of the major themes in movement science which keeps on coming again and again, and it kind of gets a new birth with every new model we have, is the idea of optimality. So the idea is that human movement system comes up with optimal solutions, and we know from Nikolai Bernstein that Nikolai Bernstein posed this degrees of freedom problem where they are infinite similar degrees of freedom in a human body. So, for instance, when you look at our action, we need to produce a very, very finite action. For instance, for us to touch our nose, but there are multiple ways we can touch it. So, if we just touch with a straight finger, it has few solutions. But if we involve the whole hand, then there's a lot more ways your elbow can be at infinite number of points when you touch your nose, for instance. So how do we know how to touch our nose? And that's the reason we are not able to repeat that action. when we talk in terms of the space of muscles, we have a lot more muscles than we have joints. When we go to muscle fibers, we have even exponentially larger number of muscle fibers. And when we go to neurons and clusters of neurons in the brain, we have infinitely larger number of neurons controlling those few muscles and very few joints, which need to be controlled to touch our nose with a fingertip. So the question is that how does the whole system select how to do it? And does it even select, a particular solution? And the idea is that somehow your internal system has parameters and is able to optimize those movement. And what we do is basically an optimal movement. That optimality can be cast in terms of joint torques. It can be cast in terms of energetic constraints. It can be cast in terms of any variable which you can model in your physical equations. And this idea of optimality has been very influential. We are still living in the cybernetic world in some ways. So with Norbert Wiener at MIT, with a very good intention, he is called father of cybernetics. The idea of how to come up with the control and communication in machines. But if you look at the title of the book, it says cybernetics or control and communication in the animal and the machine, right? It's a very technological, engineering heavy perspective about machines and similarities with the human body. And Norbert Wiener did not differentiate much between the two. In fact, we have a general tendency to not differentiate between the two. And we somehow have an internal belief that we can make more and more complicated machines which are more and more human-like. Now, if you think of that has a parallel with, for instance, water bear. So when we are comparing gait between humans and a water bear, is it about the ability to move or ability to grasp between amoeba and humans, or is it about those biological substrates? Likewise, when we are comparing a human and a robot, is it the grasping action or is it the biological substrate, right? So the motivation has been to optimize those movements and to understand human actions in terms of those optimization. Very similar to how that optimization happens in a robotic system or an electronic system. And the idea is that if you do enough number crunching, you can come up with those optimal solutions. And the corollary is that our brain is doing similar kind of number crunching. Okay. And now with the advent of neural networks and huge success in artificial intelligence, in fact, there are models which pretty hardbound models which say that our visual system is basically a convolutional neural network, for instance. Okay, so people are driving deep parallels between the language models and different kind of neural net technology with the human cognition. Again, based on the same idea that enough number crunching will lead to optimal solutions, and this is what the brain is doing. But let's coming back to the role of bones and other things. Let's just question those assumptions and see if they hold any ground. So the first assumption is that our bones serve as a rigid framework, and on those bones are soft tissues, and it enables liver-like movement through the skeletal muscle activation, right? And once you have that assumption, we can talk in terms of changing the joints, and we can describe all the movements in terms of a joint space, right? And we can cast the control problem in terms of those joint space again. And muscles basically have a function of controlling those joints. We can describe that in terms of the liver system. And you have three different kinds of liver system, the first, second, and third liver systems, based on where the fulcrum lies with respect to the effort and the load arm. So we have neck, for instance, which is a first-class liver. We have our ankle, which is a second-class liver, and we have elbow, we have a third kind of liver. And when you look at our musculature is very specific to these three different kind of liver systems. That's the assumption. And this assumption has a implication. The implication is that it is derived from a machine metaphor, from the idea of solid objects. And if you look at Leaning Tower of Pisa is one of the seven wonders of the world. And why is it one of the seven wonders? Because it is leaning. Now, what's great about leaning? because we understand that if an artificial object leans, it has to fall, right? But this object has not fallen yet. That's why it is a place we visit, right? Would we ever go and visit a leaning elephant? We will not. A leaning human, not. In fact, we lean all the time, right? Nothing special. So it's impossible. Leaning is an impossibility for an artificial object, but leaning is a possibility in human. In fact, we can be upside down, right? So the same mechanical principles, which basically do not let the leaning tower fall, let us, lean and do all sorts of acrobatics. So the question is that can we actually apply these liver models the way they are in the human body, or they're not fit for a closed chain kinematic system like the human body? We'll see it later. But for now, the take home is that we can do all sorts of things that artificial objects cannot do, which defy a lot of these simple engineering concepts. One of the reasons is that because we can produce forces internally, these objects cannot. A second, relevance to the same assumption is of a building. So why do we build these buildings from ground up? So we have pillars, and we have, for instance, in this structure, you see beams. So beams have a very different function than pillars. Pillars are under tension. Pillars are under compression, and beams are under tension, right? So we have vertical pillars and we have horizontal beams, and that's how we design our buildings based on beams and pillars, right? Now, if I ask you to make this building, let's say horizontally, and lift it once it is done, we normally don't do that. Why? Because when we pour the concrete has to settle down and take the compressive load so that it can take that compressive load later on, right? So we are building this building to keep the future in mind. And as soon as there's an earthquake, the building falls or crumbles, right? Because it cannot withstand the components which are to withstand tension cannot withstand compression, and that the components which are able to withstand compression cannot withstand tension. This is a little different than a tent, for instance. In a tent, you have a very continuous system of tension and compression, and a tent can withstand a lot of perturbations like an earthquake. But at the same time, you cannot build a 10-story tent, right? Tent has another limitations. But tent definitely is not so direction specific as this building is. Now let's see how do we create human babies. Now, when a human baby is being created inside a mother's womb, the baby does not know which side is the sky and which side is the ground. I mean, of course, it knows like through biomechanics, but the thing is the growth of the baby is independent. Because while the baby is inside the mother's womb, the mother might be doing all sorts of acrobatics, while also being pregnant. So now the baby has to develop not with respect to the gravity. The baby has to develop in all directions, withstand all kind of forces. The baby doesn't know what comes next. So, and this is the same story with the formation of every life form, uh, which is direction independent, because the function would be directional independent. Once once it is alive. So there's some kind of mismatch between our assumptions and in which how the body develops and how the body functions when it comes to the idea that basically we are talking about a load fulcrum model of movement. Let's look at the second assumption. The second assumption is Roskam's razor, the idea that we can selectively study a part of a system, uh, understand that part, and then combine everything together to integrate, and that's when we would have understood the whole system. And of course, it has led us a lot of understanding, but we are hitting some limitations with that. So, for instance, in this case, you would see a map of a brain with various kinds of functions. Each studies individually and finally integrated as a whole. The question is that are these functions actually as independent as we assume they are when we study them in the lab? And we now know that they are actually not. This is again motivated by, our assumptions about man-made objects. So for instance, you can have a car, you can take out each and every part of the car, and then understand the functions of those each and every objects. For instance, in this case, we can understand the function of the wheel. A wheel rolls, and we put that wheel back in the car, and the wheel helps the car to roll. We can sit on a chair outside the car, It helps us, sitting. We can put the same chair inside the car and we can sit inside the car, right? So most of these objects, when you take out of the car, maintain their function. If not alone, then in combination with certain other parts, and you can all put together it is a car, right? In fact, that's how our modern technology works. We mix and match things across different kind of objects, right? An air condition is an air condition in itself, and it can be also put in the car. It's not the case with human body or any life form, right? Each and every component is intertangled with other component in ways that it cannot function independently. As well, it has no other function in the world in itself. Like, what's the function of the neuron? Like, outside the human body, for instance. So the function is very context specific, as well as the function also changes, within the body. And that's a reason, for instance, a car cannot move. If you remove the tire, the car doesn't move, for instance, right? Or you can have something choked in the carburetor, the car won't move. Or you can have a number of reasons the car doesn't move, right? It's very hard to pinpoint death, for instance, in humans or any organisms. Like when does a human die? Like what place does it die? If a heart stops working, is the body dead? Is the heart dead? It's very hard to define death, for instance, in the case of organisms. That's our second assumption. Let's look at a third assumption. The third assumption is that our nervous system is representational, which means it is capable of sensing and predicting, sensing the world and predicting the state of the world. So the idea is that your eyes are like a camera which can take in the signals. The signals are casted. We make a representation the way a computer does. We do all sorts of computations on those representations, transform those as outputs. This is a computational model of cognition. Again, drawing rich similarities from how the computers operate, where you have an input signal and an output signal. And we often cast, not so much in ecological psychology, but in neuroscience, we cast our stimulus as, or surroundings or our interactions in terms of signals, right? So, for instance, we talk about uh, so simple question is that is sound a signal? Okay. Is sound really a signal? Or a signal is a signal when we have a device like some kind of a membrane that converts into, for instance, an electrical pulse. At that stage, it becomes a signal. Or signal exists without, the observer. So what exactly is the signal? Is sound a signal? Is sound a mix of signals? But when you actually look at sound is basically fluid, right? Air is a kind of fluid, and when it hits on ear, it's a fluid hitting the ear. We can talk about signals when you're talking about single neurons. Even then, we can question that idea of signals. But we have been casting our questions in terms of signals. And one of the challenges it raises is that if we think in terms of signals, what we get is signals. Okay. When you look at the neurons, for instance, on the other way, there's a very different structure between how microprocessors are and our transistors are laid and how neurons are in the brain. We have billions of neurons, each neurons with thousands to tens of thousands connections. While those connections themselves have temporal variance and spatial variance, they don't exist the same way. We can think of diseases, for instance, where you have the same kind of neural structure, but at the same time, the properties of your neural sheath is changing over time, right? The number of these connections are changing, day and night, every moment. But we still have certain functionality, certain memories, things intact. So is it about their organization? Is it about their connections? I don't think we still have a concrete idea that what is it about the neural mush which is actually preserved. Okay. Unlike semiconductor chip, where the structure itself is preserved and that storage is very much dependent on that structure. Okay. So that's the third assumption. Our final assumption is basically about the physiology, about how we measure physiology. And our current models of the physiology and how we measure things are ergodic, which means that we assume that when we record from a large number of individuals or the same individual across different times, they give the same results. So, for instance, why do we have multiple participants in a study, right? Because we think, or we have we have a perception that if we study enough number of subjects, we know we can study a phenomena. So the question is that to study a phenomena, do we need to study one participant across the lifespan, or we do need to study multiple participants across different, like a transactional design, or we have cross-sectional design, sorry, or we study 100 neurons at a time, or do we study one neuron for 100 time points? How do we actually design our studies? And most of our statistics is actually the product of early work in thermodynamics, where scientists face the problem of gas molecule in a chamber. So you have a gas molecule, and each gas molecule is different, but we are interested in the bulk property of the whole gas. So we assume that each and every particle will go through each and every part, in a chamber, and we average it across time. So we assume that each particle will travel across each space at some point, which means that we study 5 particles at a time or one particle across 5 different times. If that t tends to infinity or the number of particles tend to infinity, we will get the same properties. And that's basically our assumption about disease and conditions as well. And here I will drop like a question which I have not still been able to answer myself. With all the frequent statistics and all the beautiful insights that it has given us, the question is that how much sample size is enough? So for instance, let's assume that there are 20 million Parkinson's patients in the world. You do a study with n equal to 22, and I do a study with n equal to 2. In the larger scheme of things, n equal to 22 and n equal to 2 are both infinitesimally small, or do not, have any parlance with the whole number of Parkinson's patients. So why is it a sample size of 22 better than the sample size of 2? Okay. I'm not talking about the statistical assumptions here. I'm talking more in terms of our ability to understand a particular phenomena. Okay. So that's a concept of ergodicity. And you can see the simple demonstration here on the curve on the right-hand side here. So you have these 5 different trajectories. We can have a time average of one trajectory, which is shown in green shaded area, or we can have 5 different trajectories and we can monitor the trajectory at one time point and we can average over the ensemble. And typically we assume that the finite time average and the finite ensemble average would be the same. And that's the basis of most of our statistics, modern statistics, or our experimental designs. But let's do a simple experiment. Let's start with coin tossing. So on the top left, you have a coin toss. The values, so you have 5 different coins, and the circles in the bottom on the line and the above, they are basically heads and tails respectively. So you can toss a coin n number of times, and you can see that sometimes it will be heads, sometimes it will be tails. And if you toss that coin infinite number of times, what we know is that the means will converge towards 0.5 and 0.5, which means the probability of heads versus tails will be 0.5. Alternatively, we can take n number of such coins, and we can toss them only once each. And over time, what we will see is that half the coins would be heads and half the coins would be tails, right? So there's no ambiguity between time average and ensemble average. And that's the reason we have multiple subjects in most of our studies. But let's make this process a little more complicated. Let's start with the first order autoregressive process in which there's some dependence on the initial condition. So if you start and you sample each trajectory when it is the beginning, there's a lot more difference across the trajectories. But as the trajectories evolve, they become more similar. And that's when whether you study one trajectory or whether you study 5 different trajectories, they're not very different. Okay. But if you make a process a little more complicated, let's say in this case, you have a pot in which there are 2 marbles. One is red, one is green. You are blindfolded, you put your hand, take a marble out, and whatever color the marble is, you put one more marble of the same color. You can do this experiment or simulate it, and you would see is that depending on the first few moves, sometimes the pot becomes completely filled with red marbles, sometimes with green marbles, sometimes a mixture in different proportions. So when you look at the probability of now pulling up a green marble from these pots, the probabilities are widely divergent. And as soon as they're divergent, when you look at the one trajectory in time and you average it versus when you average across all the trajectories at some point, there's no match. Those two basically diverge. And the divergence becomes even more and more when the process becomes even more initial state dependent. to an extent that we cannot average them, and we cannot understand the properties of the system by studying more of those systems. We have to study each of that system separately, or we have to come up with properties that basically are same across time in each of those systems, right? Certain kind of dynamics. So it gives us a hint that the only thing you can study is basically the dynamics, or the dynamics evolves, but not exactly where it evolves, or what exactly it is at certain point. That won't be stable. If at all, it's only the dynamics which might give us reproducibility. So to summarize, we had four assumptions: that bones have a rigid framework, the movement system is decomposable into quasi-independent components, the central nervous system is representational, and physiology is ergodic. Now, if you go back to the example of an amoeba, or if you go back to the example of a tardigrade, we see that in those, the bones are not, there's no rigid bones. You cannot differentiate the leg of a tardigrade from its body by bones because it's just an extension. In an amoeba, the differentiation is even more difficult. There's no representation because there's no central nervous system. You have a single cell working as an eye but functioning. And when you look at the movements of an amoeba, we have now even enough evidence that the movements of amoeba and microscopic organisms are non-ergodic and non-reproducible in time. We call them anomalous. And there's a whole science of anomalous movements in statistical physics. So as soon as we drop these assumptions, the distinction between the humans and bear and a water bear evaporates. Now the question is, when the differentiation evaporates, how can we bring them under the same umbrella of study? So we have the fluid assumptions. So the fluid assumption says that the body is a tensility structure. It has compression and tension elements which are in balance. We know from ample amount of work, especially by the beautiful work of a scientist called Donald Ingber at Harvard, that how even single cells have this tensility structure and it responds to mechanical stresses, and that's how a lot of cell signaling happens in the body, for instance. We already know that a lot of these organisms like amoeba and tardigrade have a tensility kind of structure, which is form of two different kind of proteins, one more rigid and one less rigid. The second assumption is that the interactions are not additive, but the interactions are multiplicative, which means that our final statistics is not Gaussian, but it's basically non-Gaussian. And now we know a lot of data in human physiology that most of our signals, what we record, are not Gaussian, they're non-Gaussian. Whether you look at heart rate, whether you look at brain signals, you look at movement, most of them break the assumptions of additive processes. They're mostly multiplicative. The third assumption that the system is non-representational. So as soon as we assume that the system is non-representational, but there is some other way in which the brain and central nervous system operates. By the way, I'm not saying that it cannot represent. It can represent, but how it operates is not representational. As soon as we assume that, then we can study and put the same frameworks to study a bear and a water bear. And the fourth and final assumption is that our physiology and performance breaks ergodicity because of non-linearities due to multiplicative interactions. So we cannot generalize from group level to individuals unless we control for the dynamics or we look for the dynamics. Okay, if your observations are breaking ergodicity. So I know that this session was had two parts. I think we also need to have interaction based on that. I would show you evidence for each of those, but I would like to stop here. And maybe we can have a different session for going through more and more evidence in favor of these. But I think I'm here at a point where my objectives have been met with respect to my presentation, where I wanted to cast these assumptions and and emphasize how when we leave those assumptions and embrace new assumptions, we can have a science which incorporates all those organisms which behave and function seemingly like us, but we have excluded them from our understanding, and we can understand more holistically, the life forms using more fluid-like assumptions, given that they have a fluid-like existence.
So this is a finish of the formal part, but you can show us some other stuff, I guess, right? When we ask for it.
Yeah, sure.
Okay, so let's open the floor for questions and discussion. Usually takes a while. I wanted to ask you a question which would be maybe a very concrete illustration of how the four assumptions that it is reasonable to make, as you have shown, how they differentiate, for example, looking for early signs of some disease or
Okay, early signs of disease. We have it here.
pick one question, but it
Yeah,
can
let's
be
pick. Let's pick.
or repair after disability or after
Yeah,
injury, whatever. But
let's pick early signs of disease, and here you are. So we have now multiple, studies, and not myself. It's basically mostly the invention of a statistical physicist called Ken Kiono. He's in Osaka University, Japan, and my close collaborator. So basically, the idea is that can we move from Gaussian to non-Gaussian statistics? So in this case, this is a method to identify non-Gaussian fluctuations in physiological signals. And what we are doing here is that in this case, you have center of posture, people are just standing. On the left-hand side, you have a plot of a younger participant. In the middle, an older participant. On the right-hand side is a Parkinson's patient on medication, right? And from so ignore the ranges on the y-axis, but think of all these curves as curves at different scales. So bottom ones are short scales, and the ones at the top are basically the one at the top are short scales, the one at the bottom are longer scales. So what this method is doing, it is parsing your fluctuations across different scales and then looking at non-Gaussian behavior at different scales. So when you look at the younger participant, when you go from shorter to longer scales, short at the top, if it is exactly in the bottom, like a camel hump, that's basically normal distribution because it's in logarithmic scale. And on the top is basically the more peaky it is, the more non-Gaussian it is. So you will see at the top, there's a non-Gaussian fluctuations across very short scales. They are at the level of short latency reflexes. But as you go towards long latency reflexes and compensatory adjustments, they are more like Gaussian way. But when you look at a Parkinson's patient, and same with old, by the way, the old, healthy older person is very similar to young adult in terms of their Gaussian profile. But when you look at a Parkinson's person, there's a lot more non-Gaussianity at smaller scale compared to larger scale. And even at larger scales, you see a little bit of increase in non-Gaussianity compared to a younger and older participant, right? What this is telling is that there's a lot more processes in. So how does Gaussianity arise? It arises through interactions, through multiplicativity. The more multiplicativity is, the more non-Gaussian interactions you will, or product you will find of a particular process. What it hints is that the difficulty of assuming a posture in Parkinson's patients is recruiting more and more motor control processes or events, right, which is creating these non-Gaussian fluctuations. And we are working towards using these as a signature of a compromised postural system. We can find a similar thing. I don't know. I have it here, but we can find a similar thing in heart rate, where we can distinguish between with a very high accuracy between a healthy adult and a person with a chronic heart failure. In fact, if you think about it, uh, the person who gets a heart failure, let's say arrhythmia, it does not happen. Arrhythmias don't happen in just one day, right? They build up over time. So a 35-year-old might have signatures of a heart disease, which will finally, lead to us to a catastrophic event at the age of 55, right? But when you look at that heart rate time series or ECG, the same event which will happen, let's say, 100 times in a day, which will lead to a catastrophe at the age of 55, would be happening at the rate of one or two a day or one or two a month. So the question becomes, how do we identify those one or two events? When we go with the assumption of normal distribution or normality or additivity, we remove that as an outlier. But that outlier has all that information about the disease. So then we have to embrace methods like this, which focus not on that outlier, not on on that bulk, but actually on that outlier, and is able to identify that outlier even when it does not exist, or it exists in a very little, quantity in the distribution. So there is a growing amount of literature targeting these non-Gaussian signatures, for instance, to identify disease. Also to understand constraints on posture. So for instance, you have a difficult posture. You can make a healthy person behave like a Parkinsonian person if you increase the instability, right? So what do we do when we are unstable? We kind of freeze our posture. And when we freeze our posture, we also instigate other motor control processes to stabilize. And that's when you see increase in non-Gaussianity at shorter time scales, resembling what we see in Parkinson's patients, right? So then we can understand Parkinson's not just as a condition, but also as a mechanism where the person who has Parkinson's is actually ultimately trying to cope up with a deficit. What we measure in a disease is not a disease; it's also how a person is actually adapting. And there's a very thin boundary between where is that adaptation and what exactly is the manifestation of the disease. So this helps us cast that disease also, it lets us look at the disease from both sides as an adaptation as well as a deficit.
Well, thanks a lot. More questions? People in the room. When I was reading your paper, I was also thinking, have you tried to do any of those multifractal cascade measures on animals handling tools?
Yes. So I myself have not. Okay. However, Damien has a paper on phasmids. Okay, and posture and phasmids.
Damian?
Yeah, Damien Kalty-Steven has a paper in PLOS One on phasmids, and what he has shown is that those multifactorial fluctuations have the ability to explain a lot of phasmid behavior. There's a paper by Ken Kiono on C. elegans, okay, and C. elegans movements, and he has shown that there's a strong relationship between these fluid-like movements and sugar concentration or sugar uptake in C. elegans. Okay. So that's there. Yeah.
I meant, kind of direct comparison. If a human, a bipedal human, does a similar thing with a stone, then macaque or whatever who bangs the.
There's not from a fluid perspective. Reason being, for this kind of analysis, we need longer time series. So, for instance, Dorothy, my PhD advisor, while she was working in Brazil, they tried putting force plates where monkeys used to hit nuts. So they were able to record some peak forces, but monkeys don't come there and stand for a long time. I personally would love to, bring cows and buffaloes and like goats in my lab and ask them to do, or just let them, feed on force plates and do things like that. Unfortunately, I do not have the facility right now, but I completely on your side with like we need more facilities and we need more chances to study all sorts of organisms using the same kind of machines and the same kind of paradigms.
I don't know how to do it. What would be a meaningful contrast? Maybe I'm thinking too much in a sort of one difference.
I mean, we don't necessarily need to study a bipedal human, right? Yeah, but we don't necessarily need to study a bipedal human. We can study a crawling baby and a crawling monkey. I mean, or we can ask a human to be a quadrupedal. Humans can walk quadrupedally as well, right? So we did. So that's that. But the thing is, I think there are conditions in which there is a problem. For instance, I mean, so one of the reasons I like suprapostural coordination in my paradigms is because most of the diseases hurt your ability to do things supraposturally, right? So whether we are talking about stroke or Parkinson's or extreme old age, the most compromise you see in our ability to do something more while we are standing, or something more when we are already doing some things. The ability to stand and multitask or concurrent task, that's the ability gets hurt most. And that also has a lot of clinical implications because that's when you fall most. And we know, for instance, that hip fractures are very common in old age, with almost 50% of 3 month mortality. So given the relationship between the suprapostural coordination and clinical aspects of that, catastrophic events for that, uh, it makes it a very attractive kind of behavior to study across across the spectrum of human abilities. You know.
I don't want to monopolize the floor. I still have a bunch of questions also relating to our work in the lab, but do you have any? If not, then I will shoot, okay? So there is one very important concept in your paper which appeared, which seems to be gaining importance also, which is this sense of agency. And at one point you talk about the sense of agency as it is developing, and which requires sort of, I think, perceiving the relations between our own movement, the kinesthetics of our own body and the effects in the world, right? It's a very, very complex variable that we have to perceive, yet we pack it into this one concept, sense of agency. And I wanted to, maybe even to, to trace how you think about it, the development of it, or the feeling of it. And can we capture it with measures of multifractality, like the phase transition, for example, between when we have this sense of agency or not have this sense of agency?
Okay, so I think regarding the issue with agency, you know it better than me because you have been thinking about it for decades. Okay, the origin of agency. So I'm not in that shoe to address agency, with that concreteness. What this allows is multifactoriality, or just thinking in terms of scales. The first thing it does is it takes away a specific scale from agency, which means that it lets us see that agency is not specific to a scale. So, for instance, when I move, when I initiate an action to grasp, a coffee mug, my muscles, my brain, like the central nervous system, has to give, signals, or you have this action potentials, you have your muscle contractions. But that muscle contractions doesn't happen in isolation. That muscle contraction has to have a whole metabolism behind it. That metabolism has basically cells, firing rapidly, and you have ATP generation, which is happening at the level of like some milliseconds, like nanoseconds, and at dimensions like that. So the coordination is happening just for this action from that nanosecond to that second, right? So the question is that then is that movement about this action which we can observe, or is it about the metabolism, or is it about the metabolism is ready to go, it is just waiting for an action potential from the brain? So at which scale is there the agency, right? And it's not that metabolism is always there. We don't know. We can do modern neurophysiological recordings and say, right, you know what? I can record from your brain a signal which says that you were planning to move your hand a few milliseconds before that. Of course, yes. But that metabolism was also happening a few milliseconds before that. So was there a connection between that metabolism and my brain? But we do not know that connection because of the action potential has not traveled yet. So there's this kind of entanglements across the body, and each of those entanglements is across all those scales, which makes it hard to pinpoint. So I think what multifactoriality does is right now the best I can say is it casts a light on that multi-scale nature of intentionality than actually doing something more right now. I think Damien is a much better person who can answer this. But my understanding is limited to intentionality as multifactoriality helping in thinking in terms of scales.
But I remember this very old, kind of old paper by Dotov and somebody else was there.
Chimero?
Tony Chimero. And from what I remember, this is what they tried to grasp, right? This
Yeah,
kind
it's
of
I think you're talking about ready to tool versus tool to ready or something of that sort, right?
Heidegger was in
Yeah.
So yeah, I just think it's a really promising avenue, I think, for capturing, because we then don't have to answer those questions that are pestering us about, what is first, the movement or intention, the intentional movement, where is free will, etc. But we can calmly just say, okay, those signatures of movements are correlated with those feelings of being an agent. And it tells us a lot as well. I mean, we don't have to solve all those super hard problems in order to have it have some use of the measurements, right?
I agree with you. I agree with you. I am more clinically motivated right now. So, for instance, let's say freezing in Parkinson's, right? The problem of intentionality in Parkinson's, like ultimately, there's a divide between intentionality and action. That's what is happening in Parkinson's, right? So now, if one has to address it, the root cause of it, or at what scale it is happening, of course, we know the physiological issues. But where exactly is the gap between the intention to move and movement? Is it the signal? Is it the metabolism? Is it the, and this can happen across all levels, right? We have not simulated certain conditions. For instance, you have this mechanism in cells where, once an ATP is metabolized, right, you have the waste products, right? That waste products have to be transported and taken away from the cell, right? Let's say we block that process. We will see very similar kinds of behavior. We do not know probably disease of that kind, but there are multiple ways which can be targeted to understand these, in terms of the physiology. So I'm personally getting more motivated to play with physiology and across scales and understand the diseases more. And that's where being able to think in terms of scales helps more than traditional, kind of calcified ideas.
But would that push you towards pharmacology as well?
So right now I'm limited by what I can, do myself with the current support in the lab and things. But yes, that's a plan. Ultimately, to go to pharmacology as well as to go to more extreme disease models.
Mhm. Yeah, because of course, well, the environment is so much underrated, but of course it can do only as much, and it usually requires much longer time in order to retrain, for example, right? Something like that.
Right.
But I wouldn't lose this from the focus, both.
Yeah, right. But with the question that, how do Parkinson's people behave in space? Now I'm actually very curious to know, do Parkinson's start having problems swimming in water? I haven't looked at it yet, but as soon as this, session is over, that's the first thing I'll search for. And I think a lot can be, we can understand those diseases a lot more, thinking about the environment, for instance. And fluid lets us think about that environment, because when we think of in terms of rigid bodies, we think less of the environment. But as soon as we go into the fluid-based thinking, we talk about environment more and more, because there's a subtle boundary between the two.
I don't have. I think Susan's question was connected to gravity somehow. Victor, yeah.
Yeah, I have a bit of a meta question, if that's okay, because I was wondering about like one of the things that people in the context of dynamical, in general, this dynamical approach, what philosophers of science, when looking at this kind of like approach to understanding cognitive systems, worry about is the kind of explanations that seem attainable within this approach. And I'm wondering because like when you explicitly reject decomposition as one of the possible like assumption, or as one of the assumptions of how to think about those systems that you're interested in, it seems to limit the ability to provide the kind of like mechanistic component-based explanation that are the most prominent, I guess, currently in biology or in psychology as well. And I'm wondering if you could speak to that, if you think maybe this kind of like explanation would still be appropriate, or maybe you're more looking for a kind of like a holistic explanation, but then is such a holistic explanation attainable if we don't know all the details about the system that we're studying? So I'm curious, like, what's your perspective on the kind of like end product, basically, of this approach?
So I'm not ignoring, the biological substrate. In fact, I think it is about biological substrate, but I'm recasting the role of biological substrate as a constraint in this fluid interaction rather than that biological substrate as an end to something. Okay. So when I'm proposing a fluid metaphor, the bones are casted as a more calcified, those objects which are more under compression than actually. So when I gave the example of, moving away from the framework of bones, just carrying the muscles and the role of muscles to move those bones, I'm not denying the role of bones, and I'm not asking not to study bones. We are reframing that it's a tensegrity kind of system, for instance, where bones are in compression and muscles are in tension. It's more a continuous system which has a fluid-like motion. Then the question becomes, how do bones support that fluid kind of motion? And when you study that, you are studying the properties of the bones themselves. So for instance, now we know that when you lose calcium, for instance, the bones are decalcified, right? They have reduced compression strength. And now we know, from that we know how a tensegrity structure, for instance, will behave when bones are decalcified and when their ability to take stress is low, right? Take compressions is low. But then we will be able to better predict the overall properties of the body, or for instance, when the body will break, okay, compared to when we are just studying bones with a rigid body framework. Because then we are not able to relate the properties of the bones with the properties of the whole body dynamics. So I'm all for studying exact properties of the composition, but how that property relate to the overall coordination or to the overall function. So I didn't go into the details, but because I wanted to be more interactive in the later part. But for instance, I'll show you a tensegrity structure. So you have a typical building structure, one-dimensional, or you have these tensegrity structures. This is a very simple tensegrity structure, a toy model, where you have these objects which are under compression, these rods, and then you have this thread which is in continuous tension, right? And now, when you think of how the forces are transmitted, now we have ample evidence that actually in the body, the organization is like this and not like an open kinematic chain. Now, in this case, when you're looking at the properties of the bone, it will have a global consequences of what would happen. In the traditional model, it will have a local consequences. But in this case, if your bones of your hand, for instance, are weak, that will define how you move, because you have to coordinate your hands with your legs as well while moving. And that will lead to global catastrophic events. And now we know, for instance, that people with the knee osteoarthritis, or for instance, ankle instability, it's not that it's a localized problem. It has like cascading events, in coordination in terms of disability across the whole body. But that can be understood better if we can have these more, whole body or fluidic models, and relate that property of that bone to the whole structure. So if it's clear enough.
Yeah. Thank you very much.
Right. Yeah, we are not talking about abstractions here, and that's the reason the next talk, if I give you in 5 years, I want to be able to talk extreme physiology with you, like real substrates, real phenomena.
Okay, you are invited. But I just have a remark to Victor that I think this touches the problem that we are really grappling with for a long time. You know, if you start with dynamics, then you treat, let's say, components or parts of an organism as a constraint. Then you have a question. Okay, so one bone is a constraint, and this bone is interacting with this other bone, which is also a constraint. And now you have the compositionality of constraints that's very, very complicated. We have the same problem with language, you know, when we treat words and utterances as constraints on interaction. But then we would love to have grammar as well, just like, I don't know if it can be translatable to grammar of movement, maybe not so fast, but you know, when you have two words that are constraints in an interaction, their constraining properties are non-trivial, right? Because we do not know how to talk about compositionality of constraints too much, and it's funny how this problem is really similar when you talk about the skeleton or and language. So when you think about this fluidity, it's very nice stuff. Any more questions? If not, Madhuri, do you have any questions to us? More than you had?
No, I mean, we will definitely like to work together, you know, with some of your framework, especially when it comes to speech and, you know, other more what should I say, even more fluidic human abilities. But yeah, no questions so far. I mean, you get me. Some of the questions got me thinking more about some of these things.
That's great. We
Yeah.
are going to move probably more towards also movement. Julian wanted to be here. He's very happy that we are recording this, but he's going to study dance improvisation and contact improvisation, and at the same time the feelings of agency that people have, and so we are. That's why my questions, you know, are very. We will be probably really looking for your methods, and it would be wonderful to have your expertise.
Sure.
Oh, there is a question also. Go ahead. Oh, we cannot hear.
Yeah. Yeah, please go ahead.
And you are not muted, so something is going. Can you hear, Madhu?
Yeah, I can hear you.
Oh, we cannot hear.
No, but Madhu can hear us, I don't think.
Can you hear the question, Madhu?
Yes, I can hear you. Thanks.
Yeah.
Okay, it was just really, first of all, to say thank you very much for the paper, which I found very revealing. But it might be polite for me to introduce myself first. My name's Mark Doobie, and I'm from South Africa. And I've been working on these kind of ideas about embodied cognition, movement, dynamics, systems theory, what have you, for some time now, from the viewpoint of a musician. Which may or may not be interesting to people, but I just wanted to say that this whole idea of defining cognition in terms of human understandings of intelligence, I found that the way that you laid that out in the paper very appealing, very, in a way, digestible. One has to wade through a lot of literature to try and find something that clearly shows that intelligence, if we define it in human terms, becomes an exclusive concept. And the way that it strikes me that you've dealt with this is by including all kinds of actions from the smallest unicellular organisms to human beings without saying without falling back on the usual definition of intelligence, or the ones at least that I know about, which claim that humans are much more, well, understandably complex, but more intelligent. And I think it hinges on, again, the way in which we define intelligence or cognition, if you like, and from what perspective. So I don't so much have a well-formulated question, but I just wanted to say thank you, because there's a lot in this paper that resonates with the work that I'm doing regarding embodied cognition in musicianship. The
Right.
problem with this is that musicologists, I suppose I could claim to be one slightly, tend to think about music in terms of products, in terms of end results, in terms of whether they are recordings, whether they are sheet music. They tend to think about them in objects. In terms of objects, I think it's more interesting perhaps to think of musical performance as a set of processes that are unfolding, that are actually enormously complex. We haven't got to anywhere near to understanding how complex and interrelational these things might be. We talk about musical emotion, or people talk about musical emotion, and that's a hugely complex idea, musical expression. So forgive me, I come from a totally different field, and I've taken much too much of your time already on this, but I wanted to say thank you for kind of crystallizing this idea that humans are exceptional, maybe in the sense that we can draw on symbolism, we can draw on symbolic forms. But apart from that, again, the whole idea of defining intelligence in creatures according to human characteristics seems to me a little bit misguided. And thank you once again. I'll be quiet now. Thanks.
Oh, I mean, I should thank you a lot. Those are very kind words. But I agree with you with respect to, musical composition and coordination. I think neuroscience is not yet ready for that because our models are very information theoretical and very feedback based. And they right now, for instance, cannot explain how tightly coordinated, for instance, an orchestra is. Okay. And all those musical notes are at different scales. Okay. The coordination are at different scales. And the ability for a person with a really good musical sense, which I'm not, to be able to find flaws in it or, to correct it. So I don't think our neurophysiological models with those lags, with the feedback loops and, these individual processes can actually explain in any. We still don't. So, for instance, I had a chat with Edward Large on Beyond Phrenology a few weeks back, which is on my podcast Beyond Phrenology. And now, if I'm remember correctly, I asked like, what exactly is the music which makes it a good versus a bad music? Like, what exactly it is? Like, I don't think we can cast that question in the neurophysiological terms yet. Yeah, we can say that it has this structure, that structure, but in terms of neurophysiology, what exactly is bad music doing? What exactly is good music doing? Or why certain instruments basically go together, certain instruments just don't, rhyme together. So I don't think we have we have neurophysiology and neuroscience ready for that real experience.
Thank you.
But Madhur, weren't there some studies already about the dynamics of coordination within a musical ensemble? That's the first thing. And the second, some just, cascade analysis of music made by people. Can they say?
Yeah,
Tell
I
us
mean,
something?
there is some work. There's of course some patterns, but the challenge is like what exactly it reflects about the what, like as one of the audiences asked, like what exactly is about the substrate, the material which it reflects. We can always talk in terms of the music, right? The properties of the music. Like, okay, high fractality or, long range correlations or a wider spectrum makes it a better music. Yeah, but what exactly does that do to the physiology, right? Or for instance, why does what do we call it, like mind worms or the music which becomes very viral, like Gangnam Style or something? So what exactly is it doing to the memory? Like, how is it that some kind of music leaves such a strong imprint, and your body starts shaking with it compared to others, right? Uh, what exactly it is doing in our central nervous system? What exactly is doing to the body?
Sorry, if I
Yeah.
may, I think that's the crucial point of the whole argument, is from my perspective, is that musical experience is often broken down in the same way that you've discussed here. It's reduced to various activation centers in the brain.
Yeah.
I would argue, from my limited knowledge of the universe and everything else, that actually it's a whole body experience. And that when one detaches oneself and reflects on a musical experience, it's already a different mode of engagement, which is a complicated way of saying that when I'm playing an instrument with my colleagues, my memory of that is a different experience from the actual. Well, that's blindingly obvious, but it's not so much that they are. The recollection is a slightly different cast,
Right.
and one is stuck. One cannot. It's impossible for me as a practitioner to explain what's happening to me in the moment that it's happening, because the moment I try to explain it, it's gone.
Right.
Sorry, we're getting into Husserl here. So
No, so the thing is, I think we are what we are hinting it is a bigger challenge in how we do science. So I think so we are limited in how we can do science, by how we can frame our hypothesis. It's basically, hypothesis testing is one of the ways we know about doing science. We don't know another way right now, okay, or another reproducible way right now. So within that very limited ability to do science, we can frame only certain kind of questions. We cannot frame other kind of questions within that net. So that's a net we have right now to work with. The second thing is limitations by measurements. We can only measure so many things in the lab and so many times, right? So that's another limitation. And then we have a cultural limitation on science, where we understand that this kind of science is good or bad. So we have constraints of a scientist's career, what will let them to be able to do more science versus well, there's a very thin boundary between being a scientist and being a crackpot. Okay. So and that also differs across people's perception. So as a scientist, to have the credibility of the community in which you work and be able to get the support, you need to, satisfy your curiosity. One has to balance the limitations of the questions which you can address, right? So, and that's a reality in which we work. So I think as we develop more frameworks to do science, and as we develop more methods to record and to understand, I think we will lead to those questions. And I think we already have interest on those questions. But part of the inability to answer is coming out of these constraints which we have in our ability and our ways to do science. And we do not know a better way. And we need to be very careful, because it's very easy to lose credibility. And the biggest thing we have in science is our credibility to be able to do some things what we do really good. And the challenge is to balance that, and while maintaining that balance, to push up the boundaries of science. And I think we are heading there, but as the problems become more difficult, the challenge to do things become exponentially more difficult. So there we are.
I think it's a beautiful ending point, Madhur. You nailed it. Of course, it would be nice to actually show that it works for some good, and then we gain credibility, right? So that's something that is undeniable sometimes, and let's wish for ourselves to be able to show as much of this as we can always. Which I think you are doing really in your work very well, as you've shown us. Okay, thank you so much again, and bravo.
Yeah.
And hope to see you soon. And thank you all for coming as well.
Thanks for the invitation. See you all.
Thank you.
you.
Thank you all.
Bye.
Thanks. Bye.